Hello everyone and welcome to the Modern Java course. Last time around we spoke about GraalVM, which is at the core to today's talk about Spring Native. This time we will learn how we can create native executables from Spring applications and just how much we can benefit from this simple process. I run many servers and the costs of hosting all of them is growing. By using GraalVM, we can all reduce our resource usage and ultimately our costs. Before I proceed, as usual, the code for this and the other videos in this series is available on my GitHub page. So check out this project, start it, and follow me on GitHub. Spring Native is a project that aims to bring Spring applications to cloud-native platforms in a more efficient and streamlined way. The motivations for Spring Native stem from the increasing adoption of cloud-native architectures, which require lightweight, scalable, and portable applications that can be easily deployed and managed in a containerized environment. One of the key motivations for Spring Native is to improve the performance and memory footprint of Spring applications in cloud-native environments. Traditional Java applications often suffer from high startup times and memory usage due to the heavy weight of the Java virtual machine, the JVM, and the extensive use of reflection and class path scanning in the Spring framework. Spring Native addresses these issues by leveraging native image technology, which compiles Java code into native executables that can be run directly on the operating system without the need for a JVM. Another motivation for Spring Native is to simplify the deployment and management of Spring applications in containerized environments. With Spring Native, developers can create self-contained executable files that contain all the necessary dependencies and can be easily deployed in a container image without any additional setup or configuration. This makes it easier to package, distribute, and deploy Spring applications in a consistent and reproducible way, which is essential in cloud-native environments. Furthermore, Spring Native aims to provide a seamless and familiar experience for Spring developers who are used to the Spring programming model and ecosystem. Spring Native integrates with the existing Spring tooling and frameworks such as Spring Boot, Spring Cloud, and Spring Data, and provides additional features and optimizations that are specifically designed for cloud-native platforms. While Spring Native brings several benefits to Spring applications in cloud-native environments, there are also some challenges and limitations that developers should be aware of. Here are some of the main problems with Spring Native. Spring Native relies on the GraalVM native image compiler to generate native executables, which has some limitations in terms of language features, runtime behavior, and third-party library support. Some Spring features, such as dynamic proxies, reflection, and AOP, may not be fully supported or require additional configuration. Additionally, some third-party libraries or frameworks may not work well with native image and may require special handling or customization. Generating native executables with GraalVM requires additional configuration and dependencies that may increase the complexity of the build process. For example, developers need to specify the native image properties, including the necessary reflection and resource files, and optimize the memory usage and startup time of the application. This may require additional tooling knowledge and testing to ensure that the native executable works correctly and efficiently. Building native executables with GraalVM can take significantly longer than building traditional Java applications due to the complexity of the compilation process and the large number of dependencies and classes that need to be analyzed. This can slow down the development and testing cycle and may require additional hardware resources or parallelization to speed up the build. Native executables generated by GraalVM may require more maintenance and monitoring than traditional Java applications due to their different runtime behavior and memory usage. Developers need to be aware of the potential memory leaks, performance issues, and security vulnerabilities that may arise from running native executables, and may need to use specialized profiling and monitoring tools to detect and diagnose problems. This is a bigger problem since the monitoring and observability capabilities of the JVM are top-notch, and the GraalVM executables are not in the same league as at the time of this filming. Spring Native compiles to a native OS target. As such, it will be more challenging to target different OS or CPU architecture and will require separate CI/CD pipelines. A good example is the rise of ARM CPUs. Your local machine might be an ARM machine, but you might be deploying to an Intel production server or vice versa. This makes server migrations harder. Most Spring projects start in the Spring Initializer project, where we must add the Spring Native support option as seen here. It's the GraalVM native support option. Compiling a Spring Native application in the IDE is a painful experience. The build process is flaky due to several different reasons. The VM used for the build must be GraalVM, and there are several different places in which it should be set. It should also be first on the system path, which might be inconvenient. I have multiple VMs and multiple ongoing projects. I can't change my OS path to suit the whims of one particular build. The Java home environment variable must point to GraalVM. Again, this is the same problem for me. We need to use the native profile. This isn't a problem as it's just one checkbox in the IDE, but it's something we might miss. There might not be, these might not be deal breakers as we would often use GraalVM in the CI process. The local build might be too slow for day-to-day development. On the command line, the process of building the native image simply requires the command. This produces a native executable in the target directory that can be run similarly to the native jar. To give you a sense of the difference between Spring Native and the JVM version of Spring, check out this app, which is the Spring Native Hello World from the GitHub repo you can find in the description. This is Spring Boot app running with JDK 19. Notice the numbers on the bottom. No need to memorize them. I'll show them more clearly soon. This is the same app with Spring Native using GraalVM. Note these numbers were generated on a MacBook M2, but are consistent across platforms. The numbers on the bottom represent a huge difference. The same holds true for memory results. Here we can see the overhead of the application running in JDK 19. And here we see the same application compiled using GraalVM. Let's show this in a more readable table. These results might be hard to read. For convenience, let's go over them one by one. Startup time is 1,263% faster. That's fantastic. JDK 19 takes 372% more memory. The size of the application seems larger for GraalVM until you add the JDK to the mix. When you add the JVM size, it's almost 5 times more efficient than that. To be fair, this specific number can be reduced with module systems and JLink. or other strategies. Still, it's a very impressive number. There are many notes and asterisks that need to go with these numbers. These were on my personal machine. From my experience, typical containers are much slower, so the times will be much larger and more pronounced. The small demo and short runtime give a huge advantage to GraalVM. A larger app will show greater startup time gains since GraalVM has no JIT overhead and is pre-optimized. But in terms of percentages, the advantages will be less pronounced. The same is true for the differences in RAM and size on disk. But the big question is, why is startup time or memory size important in today's world of backend programming? The answer relates to the direction of cloud native. Cloud native is an approach to building and running applications that takes advantage of the scalability, flexibility, and resilience of cloud computing. At its core, cloud native emphasizes the use of containerization, microservice architecture, and continuous delivery to enable faster development, deployment, and scaling of modern applications. In a case where we want to push an update to a system with many different replicated microservices, we will need to replace all the old versions at some point. Every such update means computing time, and this can add up quickly. If our system is experiencing heavy load, we might need to spin up additional instances to handle the load, and the speed of loading them might be a determining factor. If a system loads quickly, we can set Kubernetes to have a low initial count of replicas because we know it can spin up additional resources quickly. However, for a slow system, we need to keep more replicas on standby and might idle cloud resources. Part of that replication process includes physically copying the image data to a new machine. The larger the image, the slower the process. DevOps engineers have reduced images to their bare bones. Literally, production images often have no tools within them, and the developer has no access to such images, all in the name of size. By reducing the size of the build, Spring Native makes the startup time of a replica even faster. Reducing memory is of tremendous importance as well. There are obvious reasons. If we save on memory, we can use more memory for features such as caching. However, in the case of cloud computing, there is an even more powerful and reachable goal. Replication might occupy the same machine. By reducing the total RAM usage, we can have more replicas in a single physical machine and scale faster as a result. Finally, there's serverless. Compiling to native lets us squeeze more out of Lambda. We can reduce the number of hot instances since startup time becomes fast. In the case of serverless, the benefits of Spring Native and GraalVM are tremendous and can save a great deal of cost. I talked about the downsides of GraalVM last time around, so check out that video for more. I highly recommend experimenting with Spring Native and examining the impact on your application. Next time, we'll go back to more core stuff and discuss threading. We already talked about Project Loom, so this will be more comprehensive. Follow through the videos to check out the full course. If you have any questions, please use the comment section. Thank you.